Well, good morning. It's 9:36 in the morning on Monday, the 17th of April, 2017. It's supposed to be Calculus 1 class, and right now I'm the only one in the room, which is not really a good sign. Already a little late getting started, and I'm the only one here. Not good. Hopefully some more will be coming in later. But in case you don't, let me be sure to say this as far as announcements go. Two things, and one of them may be almost too late, but this one definitely you got plenty of time. Student course evaluations are now open. Please get these done before the end of the term. Okay, you can wait till the end if you want to, but if you don't want to, please do them sooner rather than later. During finals week is a terrible time to try to be remembering all these little other details that have nothing to do with, your finishing the course successfully. They're just things that you need to do. So please get them done. If you want to and wait till the end, you can. But if you don't particularly have some reason to wait till the end, don't get them done now because they're already open. Okay, the other thing is the CAP exam is being given. I know this week, I know one was given this morning. I don't remember how many times it's being given. That is something that I really encourage you to do because that gives us a good measure of what kind of job we're doing, and may also give you an opportunity to write down a pretty good score on your on a resume or something that you scored in the upper so many percentile on the national exam. So please get those done as well. All right. From what my memory is and my mark in the book, we're on example 5 on it's chapter 4, applications of the derivative, 4.2, extreme values, and example 5 on page 204. And that's the logarithmic example. It says find the extreme values of the function f of x. It's this function right here. Let me get my pen color adjusted. Okay, it's this function right here. F of x is equal to x squared minus 8 log x on the interval from 1 to 4. Okay, so find the extreme values of that function on that intervals. Okay, and it says first find the critical point. It doesn't matter what you do first, but that's a good thing to do. To find the critical points, you find the derivative. So f prime of x is equal to, if f of x is x squared minus 8 log x, that would be, the first derivative of that would be 2x minus 8 over x. Okay? And we want to set that equal to 0. That will be where our critical points are. Now, one thing that should reach out and grab you right at the beginning, remember that, okay, let me back off just a minute. We want the places where the first derivative is 0 and the first derivative is not defined. Looking at that first derivative, something should reach out and smack you right in the face and say, x can't be 0, not defined at 0. Perfectly fine. The thing is, though, 0 isn't in that interval. So we don't have to worry about that. So the next thing is, where is this function derivative equal to 0? Well, let's solve that equation. What we could do is add 8 over x to both sides. Okay, and that would give us 2x is equal to 8 over x. Okay, and you can multiply both sides of the equation by x, and that would give you 2x squared is equal to 8. Divide by 2, and you got x squared is equal to 4, and so x is equal to plus or minus 2. Okay, those are the two places where your first derivative is 0. Okay, except that number 1, 2 is in this interval, negative 2 is not, but if you went back up here and look, you can't have, well, I'm sorry, look up here, x can't be negative 2 because you can't take x, when you look at this, our original equation here, our function here, x squared doesn't give you any problems at all. That's defined in all real numbers. Log x is only defined for x greater than 0. Not equal to 0, not less than 0. So x equals minus 2 is out of the picture there. It's out of the picture here. It's out of the picture everywhere, just like 0 was out of the picture here and there, everywhere. So we're not concerned with x equals negative 2 or x equals 0 because the function's not defined at either of those two values. But it is defined at x equals 2. So that's our only critical point that we're going to be evaluating. Okay? Now, what did it ask for? Extreme values of that function. So what we do, we evaluate the function at f at 1, because that's one end of your thing, f at 2, because that's your critical point here, and then, see, this is this value, and then we'll do f of 4, because that's your other endpoint. Okay? And let's see what each of those is or are. Okay? When f of 1, that would be 1 minus, and what is the log of 1? 0. So that is just going to be 1. Okay? F of 2 would then be 4 minus 8 log 2. Okay? And f of 4 would be 16 minus 8 log 4. Okay? Now, you can pull out your handy dandy calculator and find out what those values are. And I don't have one on me, but they do have it in the book. We have a student! Amazing! Fantastic! Okay? Richard's here. Okay, we'll mark this. Okay. Good to see you.
Good to see you as well. And
Fantastic. Thank you.
and almost done with my paper to turn into.
Okay, super. Okay, and then also, this is the first test, which is chapter 2, right?
Correct.
And chapter 3, do you have that test?
I do not.
You do not. Okay, let me make sure you have that one. Oops. Test 1, test 1, test 1, test 1, test 1, test 1, test 1. Here we go. So I've got to find. Why do I not have a spare copy of it? Someone must have gotten 2. This is disconcerting. Oh, there it is right there. It was stuck on something. All right, there's your test. Okay. Now, number 7, my word processing package made that prime a little bitty mark that a lot of people weren't seeing, so I did a big slash there.
I think there was a problem like that on the first test as well. It was one, do you still have my test right there?
Right there.
I can show it to you.
Okay.
It was, let's see, it was a prime, really, really small,
We hadn't done derivatives, I was surprised that there would be a prime there. There's some small negative signs.
It was a prime. Do you mind if I look at it a little closer?
Yeah,
and I'll I mean,
okay.
there it is. Sorry. I should want to be looking right over you, right here on the H.
Oh, that's a comma.
Okay.
Wait, what is it? Yeah, that's a comma, because A, comma, B.
Okay.
Yeah, that's
Well, then I'll have to rework that. Yeah. So.
Yeah.
I'm sorry.
Yeah, okay. Okay. All right. What we were just doing, and by the way, nobody doing here, I didn't have the projector on or the light first. On page 204, are you looking for that or this?
I was trying to see where we were.
Yeah, 204.
Which is what section?
Chapter 4, 4.2.
Okay. I was just remember.
Oh, that's right. You have a different book.
What's the title of the
Okay.
section?
The chapter is Applications of Derivative, and the section is Extreme Values.
Okay, so that's the same for me too. Perfect.
Okay. And it should be, and this one is figure 11. Is that the same?
4, figure 11.
Does it look like that?
No, but it's okay. I'll follow along.
Okay. You find the figure similar to that? This one may be easier to find. The previous one, this one.
Oh, let's see. Yes, no, that's figure 10 for me.
Okay. And your figure 11 is not that one. Okay.
It kind of goes down and then it comes up and then it slopes back down.
Okay. All right. We'll go with this.
I'll just follow along.
Okay. Now, I just about finished this, but I think maybe it'd be worth going back over, because you probably won't want to go back and do YouTube on this. So let's erase this for now. All right. Now, what example 5, that's what it is in this text, its subtitle is a logarithmic example. And example 5 is find the extreme values for the function f of x is equal to this. So here's the function, here's the interval of the function, and we're looking for extreme values. Okay. So let's hit this a step at a time. First, what are your extreme values?
1 and 4.
Okay, all right. You're really not too far off there, but here's what you're looking for. You're looking for relative minimum or relative maximum. That's what we mean by extremes. That's the y values. Now, the 1 and 4 are the values on which x are located.
Right.
1 and 4. But maybe not surprisingly, but you just happen to do, when you're looking for extreme values, there's 2 places that you look. One is your endpoints, which is 1 and 4, okay? And the other are your critical points. Now, what are your critical points? Okay? And by the way, what's the title of the chapter?
extreme values.
Now,
Or applications of derivatives.
derivative,
So take
okay?
the derivative.
So what you do is take the derivative of the function,
So
and
2x.
then you're looking for one of two things, whether that derivative is 0 or whether it's undefined.
Okay.
Okay, so that's what you're doing for this. You're looking for extreme values. That's either going to be an endpoint or it's going to be a critical point. Endpoints are, of course, the endpoints. The critical points are either going to be where the first derivative is 0 or undefined. Okay. Now, for a problem such as this, okay, and I plunged head on into it, and then decided I really probably should have paused and started. It's always a good idea, I think, to consider your function first. Okay? Is there any place where this function is not defined? Okay, the function is x squared. I'll blow it up for now. I was going to be writing on it, so I can't write on it, but I'll have to reduce this very shortly. But this function, the x squared part is defined everywhere. Polynomial function, no restriction. However, the second place where the x shows up is following a log. What's true about logs?
Let's see, is it that you can't take the log of -1?
You can't take the log of any negative number.
Okay.
But not just that. You can't take the log of 0 either.
Okay.
So it has to be all positive numbers. Well, certainly our interval is all positive numbers from 1 to 4. No negative numbers there, no zeros there. Okay. But I say that because I have already proceeded with the problem. And what's the next thing we do? We already know the endpoints, 1 and 4. Now we need to determine our critical points, and what are those?
Where it's 0.
Where what is 0?
Where the derivative.
Okay,
is 0.
is either 0 or?
Negative.
No, undefined.
Undefined.
Undefined. Okay. So the next step would be to take the derivative. Okay, and what's the derivative of that function?
So 2x
2x
minus 1 over 8 log.
no, 8 over
Oh,
x.
That's right.
Yeah. And Rodney's here. We got the top of the alphabet and the bottom of the alphabet. We just got the two middle ones are missing. And we got our Y chromosomes and the two X's are missing. So, okay. So there's our derivative of the function. This is example 5 on page 204 in section 4.2, chapter 4. Okay? What we're looking for are the extreme values of this function on that interval. And I'll say it again. Now, let me say this too. Student course evaluations are open, so please get those done before the end of the term. I don't mind if you wait till the very end of the term if you want to do that, so you can evaluate the entire course if you're prone to do that. But just it's real easy. By the end of finals, you're so swamped with everything to forget to do something like a student course evaluation. So please don't forget it. Please do one.
Do it on the computer too.
Yeah, and
Because
yeah.
it's a lot easier. You can get it, unless you want to be stuck with having to go through 50 pages.
Right.
How it's set up on the mobile, after it only does one question at a time.
Right.
Unless you do it on the computer, and you can do, all 50.
Yeah. Okay. Good point. I hadn't tried to do it on a mobile, but that does seem like it would be good. Okay, so what we're doing, we're looking for extreme values of the function. Okay, and this is given on an interval. There's the function, there's the interval. Okay. A couple ways to approach this. First, what are your extreme values? The extreme values are relative, maximum, or minimum, right? Okay. In fact, an extreme value would be absolute maximum, absolute minimum. Okay. Where do those occur? The possibilities would be at either endpoint, at 1 or at 4, or at a place where your derivative is either 0 or undefined. Okay? So we are going to evaluate this at 1. We'll evaluate it at x equals 4, and we'll evaluate it where the derivative is 0 or undefined. We just took the derivative. F prime of x is 2x minus Minus 8 is just your coefficient, so that leave that alone. The derivative of log x is 1 over x, so that's what I put it down here. Now we take a look at that and we ask ourselves, where is either that's equal to 0 or that undefined? Well, the undefined should reach out and smack you in the face. Where is that derivative undefined? 0. At x equals 0. Okay? So is that one of your considerations for your extreme values? It would be, but you see that's outside the interval. The function isn't even defined at x equals 0, so therefore we're not worried about x equals 0. It's not in the interval, so, and it's not even defined there. So we're only concerned where that is equal to 0. So we set this equal to 0. And what would be the first thing you would do then to solve that equation?
Would you add 8 over x?
That's what I would do. And that gives you, I'm going to write it up here because I'm running out of room down there, 2x, and these add to 0, is equal to 8 over x. Now what?
Would you multiply by x on both sides?
That's what I would do. That makes that x squared, and the x here is going to wipe out the x there. So we get 2x squared is equal to 8.
And then would you divide by 2?
I would divide by 2. Okay? And that gives me x squared is equal to 4. Okay, and that would give me x equal to plus or minus 2. So those would be our two places where the x, the derivative might be 0. X out for what? X negative 2 is not in the interval. And what's more, it's not even defined there because you can't take the log of a negative number. So therefore you forget about the minus 2. So the only point for a critical point is going to be x equal 4. Okay? So here are our three values. X equal 1, x equal 2, and x equal 4. 1 because of that endpoint, 2 because of the critical point, and 4 because of the other endpoint. Okay? So now we evaluate the function of each of those. So f of 1 is 1 minus, and what is the log of 1?
I'm not sure, but the screen.
Oh, okay.
Is it 1?
Yep. Okay. Here's a little hint. Do you remember what exponential function looks like?
Yes. The
No, that's a absolute value function. What's the exponential function? E to the x. What does that look like?
Is that how it's getting closer and closer to the 2 point?
Okay. It's e of 0 is what? E to the 0 is 1. Okay. And e to the anything negative would be 1 over e, blah, blah, blah. So that's going to 0 that way, and this is going exponentially high here. Okay, your log function is the inverse of that. So where this is a 0, 1, this is a 1, 0. And it's going like that.
Okay, so 0.
So yeah, so this is 0. Okay, so this is equal to 1 because log 1 is 0.
That
Okay.
makes sense. Cool.
Okay, so now let's do f of 2. And that would be 4 minus 8 log 2. Now, log 2 is not a number I happen to know, so I say plug it into your calculator. It's the ln2.
.6931.
0.6931. Okay, approximately. Okay, about 4.
That
F.
was just the log 2. Would you like to plug in the rest? The 8.
Oh, okay, yeah, no, yeah, I wanted the whole thing, right. You just sort of plug it in. 4 minus 8 log 2. Oh, Oh, you're using a phone rather than calculator. What's that? Oh, sorry. Well, it's in the book. Negative 1.55. Okay. Now, looking at those, I can tell of the 3 points, I got a 1 and a negative 1.55. We got either a max or a min. We just got to see what the fourth one is, or the third one is. And alpha 4 would then be 16, 4 squared, minus 8 times the log of 4. And that's going to need another calculation, one that I can't do in my head, on my log tables.
I think it's the table I don't have with my figures on the screen.
Okay. It doesn't show up here on the show where it is, but in the text it shows it's about 4.9. Okay. But your calculator should be able to tell you that when they're working properly. So looking at this, our extreme values, the 1 is not. That's an intermediate value. Okay? Your min is here, and your max is here. So that's what you're looking for, your maximum value and your minimum value. Maximum value is that, minimum value is that. And on the graph you see, here's the endpoint 1. They show this beyond 1, but they really are only interested in 1 to 4. They show beyond 4 too. So here's 1, there's negative 1.55, and there's positive 4.9 or approximately. So that's obviously the min. That's obviously the max. This one's an intermediate value, so it's not an extreme value. Make sense? Okay. So to find your extreme values, you consider your endpoints and your places where your first derivative are either 0 or undefined. Okay. So let's go to a trig function. Okay, and this shows those in the table. You don't have to do this, but it's sort of what I was just doing. And I like to do left to right. They do critical points first, endpoints. It doesn't matter how you do it. If your one and only critical point, because x equals 0 is outside the range of the domain, x equals negative 2 is outside the domain, so we only have one value of your critical points that was inside the domain, and the limits on the domain, endpoints of the domain. So this gave you your negative 1.55, positive 1, positive approximately 4.9. Obviously, this is the back, and this is way. Okay. Now, here is a trig function. All right. Find the maximum and minimum of the function f of x equals sine x plus cosine squared x on 0 to 2 pi. And they don't show the function here, so I will erase this and do it. Here's your f of x. It's equal to sine x plus cosine squared x, I believe. Yep. Cosine squared x. Okay, on the interval 0 to 2 pi. Okay. Now, to find the extreme values of that one, or actually, the way they ask this one, find the minimum and maximum of the function. Okay? They don't even call them extreme values, but that's what you're looking for still. So how do you proceed? What do you do? Take the derivative. Okay? So f prime of x is equal to cosine x.
And then negative sine x squared.
Say that one more time.
Negative sine.
Not quite. You got to do your chain rule. First take the derivative of the bigger function, which is the squaring function, the outside function.
Right.
And that would be 2
cosine
x times the derivative of the inner function, which is cosine, and that gives you the negative sine x. So I thought you were just looking well ahead and saw that it was going to be a negative, so that would make it that. Okay. Now, what do you do with that?
Can you combine like terms with the cosine x?
Okay, that's going to be a not quite that terminology, but the right concept, I think. What you're looking for is where your first derivative is one of two things.
Where it's 0 or undefined.
Okay. Now, is that undefined anywhere?
No.
Sine and cosine is defined everywhere, so products and sums, so no problem there. So we're only then interested in where it's equal to 0. Okay, with that in mind, what would you do to solve that equation?
Separate the cosines and sines.
Okay, in other words,
So
what's your,
divide by sine.
okay, what's your F word?
Oh, factor.
Oh, yes, factor, okay. So that's cosine x. The only common factor here is cosine x, and what does that leave you with?
1 negative 2 times sine of f.
Okay, I didn't need brackets. I could use parentheses. Okay, now there you have two factors. What you have is the product of two factors equals 0. What do you know? How can you multiply two entities together and get 0 as a product?
If it's
One of those entities got to be 0.
0, okay.
There's
Yeah.
no other thing you
Gotcha.
can multiply by something to get 0,
Okay.
except 0. So this tells you either cosine x is equal to 0, or 1 minus 2 sine x is equal to 0, right? Those are your two factors. One or the other has got to be 0
Right.
for that product to be 0. Well, what values of x between 0 and 2 pi, where do you find your cosine to be 0?
1. Cosine of 1 is 0.
Nah. Usually you do cosines of angles.
Cosine 90 degrees.
90 degrees would be 1, and since they're using 0 to 2 pi, let's call that
What's that? Pi, not
pi halves.
Pi halves, okay.
It
yeah.
is exactly pi halves. Because remember, 2 pi is one circle,
Right.
half a circle is pi, and half of that is pi halves, 90 degrees. Semaphore, okay. Okay, so there's one place where cosine is equal to 0 at pi halves. Any other places where it is? Between 0 and 2 pi?
Let's see. 3 pi halves.
3 halves pi, exactly. So 3 halves pi is another one. Okay, two places where your cosine could be 0. Okay, how about over here? What would you do there?
Sine of pi.
Okay, let's first solve that.
Well, you got to get the right.
Yeah.
So go ahead and subtract one from the other, from one side to the other.
You can. I'd rather as soon add 2 sine x to both sides. Okay, I'm just lazy that way. Okay, so these go out, and that will give you, I'm going to reverse the sides now, 2 sine x is equal to 1. Would you buy that? Okay, how much? Never mind. Okay,
Divide by 2.
divide both sides by 2. Okay, that gives you sine of x is equal to 1/2. Now, where in the world is your sine between 0 and 2 pi 1/2?
Would it be, let's see.
pi fourths is root 2 over 2. Pi 6 is 1. So x equal pi 6. That's one place where the sign is 1/2. Now, I don't know, do you prefer graphs or unit circles? What do you visualize best?
Unit circle.
Unit circle. So let's do the unit circle. Only I'm not going to do a unit circle, I'm going to do a 2 circle. Okay, because hypotenuse being 2. Right, okay. And sine is y over radius, so r equal 2. So let's do a 1, 2, a 1, 2, a 1, 2, and a 1, 2. Okay. So there's going to be my 2 circle. Sort of ugly. Okay. 1/2 would be the y value being 1. And this is ugly. Oh. It's here. I was doing the wrong one. I was doing the x. Okay. That's it. And that's your pi 6. Okay, so that's one place where the sine x is equal to 1/2. Now, where else is sine first positive?
All students take calculus, so in the 4th quadrant.
Calculus is cosine.
That's right. All students in the 2nd quadrant.
Second quadrant. So that'll be over here. There's the other place. There's a reference angle. So what angle is this to get us to that reference angle? In fact, it's
So pi 6 minus pi.
or pi minus pi 6, which would be
so 5 pi over 6.
exactly 5, 6 pi. Okay, I wanted you to think through it. 5 pi 6. So there's 2 over here. 5 pi 6. Okay, so we had 2 possibilities here and 2 there. Okay, and we have our endpoints, 0 and 2 pi. So this is just my dumb little way of doing. Let's do our alpha of x at each of these values. So at x equals 0, pi 6, pi halves, 5 pi 6, 3 halves pi, and 2 pi. Sorry about that. They're running kind of crazy. 2 endpoints, the 2 for cosine and 2 for sine. Okay? So let's evaluate the function of each of those. Alpha of 0. What would that be? 1.
Plus,
Okay.
oh, sorry. Cosine squared 0 is 1. So 1 plus 1.
Okay. What's sine of 0?
Sine of 0 is 0.
Yeah.
I'm sorry. So 0 plus 1, yeah.
1. That's the value there. At pi 6, okay, alpha pi 6 would be the sine of pi 6 plus cosine squared of pi 6. Okay, sine of pi 6 we've already determined to be
0.
No.
1/2.
1/2. Okay, 1/2 plus, and now we got to do cosine of pi 6. What's the cosine of pi 6? Okay. It's
0.99.
okay. Yeah. All right. I'm going to show you this little acrostic, thing I found helpful. Okay. Here's your pi 6. Here's your pi quarters. there's your pi thirds, and there's your pi halves, right? So this is 0 over 2, 1 over 2, oh wait, square root of 0 over 2, square root of 1 over 2, the square root of 2 over 2, the square root of 3 over 2, and the square root of 4 over 2. Well, square root of 4 is 2 over 2 is 1, okay? If you remember that, that's going to help a lot of things, okay? So this is pi 6, pi fourths, pi thirds, and pi halves, right?
I'm looking at pi 6.
Okay, this is pi 6, and the sine of pi 6 is 1 half, okay? The cosine of pi 6 is the same as the sine of pi thirds.
Okay.
That's why I did that one. And this would be square root of 3 over 2.
Okay, cool.
Okay. So square root of 3 over 2 squared would be 3 over 4, right? Okay. So you have 1 half plus
3 over
3 fourths. So that would be 1 1/4, right? 1.25. Okay? So we've got at least a min and a max, because 0 is 1, this is 1.25. So let's do the pi halves now. What's the sine of pi halves? 0. No, wait, sine of pi halves is...
Is that the one? No, excuse me, that's the 5 pi 6 at 0. That we,
What's that?
or no, we said that was 1.
Yeah, pi...
Or 1 half.
Yeah, sine of pi halves is 1. Okay, these are the signs. Sine of 0 is 0, of pi 6 is 1 half, pi fourths is root 2 over 2, pi thirds is root 3 over 2, and pi halves is 1. So that's going to be the 1, okay? And then cosine of pi halves, what is cosine of pi halves? 0. So so this is back down to 1 again.
Yes.
Okay, so you got a 1, 1 1/4, 1. Okay, 5 pi 6. The sine of 5 pi 6 is 1 half plus, and what's cosine of 5 6 pi? Remember? 1, 2, square root of 3.
Right.
So that's going to be minus the square root of 3 over 2. But you're going to square that, so it's
3 over 4.
3 over 4 again, so it's 1 half. So it's the same as before, 1.25.
Okay.
So this is again, so that's 3 fourths. So that's 1.25. Okay, how about 3 halves pi? Sine of 3 halves pi is?
Oh, 1. Is it 1? Or it's negative 1.
Negative 1. Okay, so that's going to be a minus 1 plus, and what's cosine of 3 halves pi?
Would it be 0?
0, so that's going to be a negative 1. Looks like we could have a minimum. Maybe, maybe not. We're not quite there yet. We got one more to go, and that's our 2 pi. Sine of 2 pi is?
0.
0, and cosine of 2 pi is?
1.
1, and 1 squared is 1. So that's 1 again. So we have a bunch of 1s. So what's our maximum, minimum, and maximum value? Minimum value is right here, x equals 3 halves. Maximum values, we actually have 2 of those, and that's these 2. This one and that one. Okay? And this graph, I think, shows it to us, sort of. Let's blow this, I don't know, maybe I want to leave it like this. So yeah, sure enough, we started at 1, went up to 1 1/4, went down to 1 again, right?
Yep.
Yep. Then we went up to 1 1/4 again, down to a minus 1, and then back up to 1 again. Okay? So we had 3 1s, 2 1 1/4s, and 1 negative 1. Sure, that's our minimum. These 2 are co-maxes. They're both your max. Okay? So it obtains a max of pi 6, 5 pi 6, minimum of 3 halves. Okay? Make sense? All right. So that's example 6. And they show all this with their table here, which is basically the same one we just did, only they do the critical points first and then the endpoints, which are fine. I mean, it doesn't matter. I just sort of like to do them in order, so that's just how I think. But yeah, you can do it anyway. So your critical points for your pi halves and 3 halves pi, pi 6 and pi 6 pi, and your endpoints are 0 and 2 pi. Now, there's no guarantee these are going to be the same, so why did they list them separately, I don't know. So anyway, you did each one of them, and the critical points is sine of pi halves is 1, cosine is 0, so that's 1. 3 halves pi was minus 1, and plus 0 is that. Pi 6 was 1 half plus that, pi 4, so we got same here, and then these just happen to be, they turn out being 1. There was no guarantee they were going to be the same, so I would have done them separately. This would have been 0 plus 1, and this would have been 0 plus 1. So yeah, it does work out that way. But the ones are intermediate. The minimum is minus 1, the maximum of 5 fourths. All right, that leads then, that's all the examples we're going to do of this one, but that leads to Rolle's theorem, Rolle apostrophe S theorem. Here it is written here. I'll blow that up for you to read. And by the way, I wanted to mention to you, the class, that this, of course, one of my best classes for sure, right? Okay, and yet it's the only class I have this term that I've received 0 papers yet, 0 research papers. I need those before the end of the term. And do you realize we've got this week and we've got next week, and then we got finals week. So the research papers need to be in by Wednesday week. I'd rather have them sooner than Wednesday week, but that's the last day you can turn them in before getting points taken off. Okay. So here's a potential paper topic. Who in the world is Rolle? I don't believe it's pronounced Rolly. Okay. Test 1, let me remind you. Oh, I think I have received all of those in now. So actually, I can return. Let's see. Did you give it back to me, or are you still working on it? Okay, that's all right. Okay, fine. Okay, but I'll be returning those to you as soon as I get the last one in. And test 2, I still don't have any of those in yet. You got one, right? What's that? Okay, you don't have it? Okay, I don't have a spare, so I'm going to have to make an extra for you if you need one. Is that what you say? What's that? Right, okay, so hang around just after class, I'll go make another copy. So anyway, here basically is Rolle's theorem. As an application of our optimization methods, we prove Rolle's theorem, and here's what it states. If f is differentiable, in fact, well, here's the picture of it, okay? If f is a differentiable function, and they just drew a whole function here, now what does it mean to be differentiable? It's got to be 2 things. Smooth and continuous, you got it. So if this is a smooth continuous function, then basically if f of a is equal to f of b, some point a and some point b that have the same values, okay, on some interval, then there's got to be some point in between those two, c, where the first derivative is 0, okay? And that's because if these two have the same values and it's a smooth continuous function, then there's got to be some other place where either this is going up and come back down, and it's smooth and continuous, and there has to be some place where the first derivative of c is 0, okay? Because it's got to be parallel to that. So there's the picture description of it. Here's what the theorem says. Assume that f is continuous on a to b and is differentiable on the interval a to b. Now, what does it mean to be differentiable? that the derivative exists. Okay? And for the derivative to exist, we can't have any gaps. That's why we have to say continuous. Well, it is continuous already. It can't have any cusp. It can't have any corners. It can't have anything else other than a smooth continuous function. Okay? So assume that f is continuous on AB and differentiable on the open interval A to B. It doesn't have to be differentiable at A and at B. It just has to be differentiable anywhere between that. Okay? And if f of A is equal to f of B as endpoints of that, then there has to be some number C in between there where your first derivative of C is 0. It's got to be, because if they're equal at the endpoints, then there's going to be some place where there's a max and some place there's a min. Or else it's going to be the constant function of that value, whatever that is. Okay? And a constant function, alpha prime of C is 0 at every point C. Okay? So that would be not that hard to prove. So there is a little proof there, well worth reading and going through, thinking through. Let's move on to example 7. And I do not believe they have a graph of that, so let's just do it here. Verify Rolle's theorem for this function. F of x is equal to x fourth minus x squared. Number 1, is that a smooth continuous function? Absolutely. It's a polynomial function. They're always smooth and continuous. Okay? And it says on the interval from -2 to 2. Okay, now the other condition here is, for Rolle's theorem to be considered, we need to make sure those have the same values. And what is f of -2? -2 to the 4th power.
-16?
Positive
16.
Yeah. Okay. Okay. Positive 16 minus
Plus
4, so that would be 12. How about at 2?
16 minus 4
is 12. So that has the same values at both endpoints. Now what Rolle's theorem says, there has to be a number C, maybe more than one, in between A and B where the first derivative is 0. Okay? So let's see if that's true. What would you do? Take a derivative. F prime of x would be 4x cubed
minus
2x, and set that equal to 0. Okay? And what would that produce?
Take out a 2, a common, anyway, you get 2x cubed.
Okay, wait.
You take out 2x.
Right. Okay.
So you get 2x squared minus
2x squared
yeah.
minus 1 equals 0. And what does that tell you?
Then you add 1 to both sides.
Okay, we'll split them up. Either 2x is equal to 0, or, so you got a product of two entities, okay, or 2x squared minus 1 equals 0. What does this side tell you?
Divide by 2, so x equals 2.
One more time.
Negative 2. Yeah. 1 over 2, so 1 half. No. 0 half. Okay, 0.
0 over anything is 0, except 0 over 0 is undefined, or indeterminate. Okay, over here,
Add 1 to both sides.
okay,
Then divide by 1 half. X squared equals 1 half.
x squared equal 1 half, so x is equal to plus or minus the square root of, well, 1 over root 2, which is square root of 2 over 2. Okay, I mean, or negative square root of, yeah, whatever. Okay. Now, all these values are in between negative 2 and 2. 0 is in between that. Positive, this is in between that, and negative, that's in between that. So we got 3 values that they're all in between, and all the first derivatives are 0. Okay? Like I said, you're not limited to just 2, but since you came up with the first derivative of the third order, you expect to have up to 3 possible zeros, and you do have 3 zeros. Okay? So they do C is equal to 0, or C is equal to plus or minus 1 over root 2, which is plus or minus 0.707. Okay, if you did those out, you'd see that. All right, now example 8, and I think that does have a graph, so we'll use it. Okay. It says show that f of x, which is this right here, x cubed plus 9x minus 4, has precisely 1 real root. Show that it only has precisely 1 real root. So how are we going to show that? Okay. Well, you can do that. You got x cubed plus 9x minus 4 equals 0. Okay? But frankly, I can't factor it. I could start using some of my techniques that I learned in pre-calculus algebra about finding zeros, and hopefully might be able to get something to work there. But it says the prefix here is using Rolle's theorem. Now, how does Rolle's theorem apply here? Well, certainly that's a continuous function because it's a polynomial function. Okay?
Would you not take the derivative of it? And then
Okay, let's try that and see what happens. Okay? The trouble is f prime of x would then be equal to what? 3x squared plus 9. Okay? Now, Rolle's theorem would suggest this needs to be equal to 0, right? But if you look at that, you see it can't possibly be equal to 0.
it has to be equal to positive 4.
Okay?
You have to include that or no?
Yeah. That 4 is sort of out of it here. See, frankly, just looking at it, Rolle's theorem doesn't seem like it applies. Because Rolle's theorem says f of a equal f of b, and there is no place for a number on this side is equal to a number on that side. Because this is an increasing function, and it's a continuously increasing function, so there is no place. So you would think, I mean, when I look at this, I say, Rolle's theorem isn't the one to use here, okay? But if you looked at its derivative of this function, you would see that that's always positive, which is exactly what we're seeing there. It's a constantly increasing function. No value you put in here for x is going to produce a negative number here. You know, they're always going to be positive, okay? Because x squared is always a non-negative number. It could be 0, but when you add 9 to it, that's going to be positive, and anything else is going to be even more positive. So that's always positive. So basically all you have to show then that f of something to the left, well, here would be an easy thing then. When x is equal to 0, the function is equal to negative 4. And when x is, say, equal to 1, that would be 1 plus 9 is 10, minus 4 is 6. It's a constantly increasing function, positive derivative. It's negative on this side, positive on this side. It's got to have a 0 in between. But the question is, it says it needs to show that it only has 1 real root. Sure, we can show it has a real root, but how does it show that it's only one root? Well, because the first root is positive everywhere. Okay? So therefore it's increasing everywhere, and if it's increasing everywhere, it's only going to cross that once. Can't happen otherwise. Now, how do you use Rolle's theorem to show that? First, we note that alpha of 0 is -4, which is what we said is negative, and alpha of 1 is 6. We said that too, and that's positive. By the intermediate value theorem, not Rolle's theorem, then alpha has at least one real root between 0 and 1. Okay? If alpha has a second root, then alpha of A equal alpha of B, and that would have to be 0. Okay? Then Rolle's theorem would apply the F prime of, okay, so you do it kind of backwards, okay? If there was another root, B, then F of A equal F of B, and it's basically what we said. That would imply that F prime of C has to equal 0 somewhere between A and B, and guess what? It can't, because F prime of C is positive everywhere. So therefore, since there's one root, that's the only root. So really, we did kind of do that. All right. Now, top of page 208. We mentioned Rolle. Here's two other characters, Pierre de Fermat and René Descartes, both of whom very famous mathematicians. Well, I say that. A decade before Isaac Newton was born, the French mathematician Pierre de Fermat invented a general method for finding extreme values. This is before calculus was invented, so he formed another one. Fermat said in essence that if you want to find an extrema, you must set the derivative equal to 0. They didn't even define derivative yet, and solve for the critical points, just as we've done here. He also described a general method for finding tangent lines, not necessarily, that is not essentially different from our methods of finding derivatives. For this reason, Fermat is often regarded as the inventor of calculus, together with Newton and Leibniz, which I never, except for here, have read that written anywhere else. Yeah, it's not. A lot of people don't think that way, but this gives pretty valid reasons for it. Around the same time, and if you look at this, they were 5 years apart in age. René Descartes was 5 years older than Pierre de Fermat, and they did correspond. I think they were pretty big buddies too. I'm not sure, but I think they were. Developed a different but less effective approach to finding tangent lines. But he did it more sort of analytically, I guess. So, by the way, Descartes, famous for the Cartesian coordinate system, named after him, but also a fantastic philosopher. A lot of people don't know him as a mathematician, but as a philosopher, one of his famous lines was, "I think, therefore I am." That was René Descartes, wow. Great mathematician. Okay, so a lot of possibilities here. And what I remember from Fermat and Descartes, and how I remember them together, I think they liked to gamble, and they did some of the early work in probability theory just so they'd have an edge in gambling. And that was the only thing they used it for. I think there were another couple. Pascal, I think, was in on that too. So anyway, later, the first, what I consider practical, useful purpose in statistics was, in probability statistics, a woman you've all heard of, Florence Nightingale, used statistics to prove that you could, or to show that you could cut down on deaths in the battlefield if you cut down on infections and increase. I mean, she used statistics in a very beneficial way rather than just making money on it. But anyway, many more paper topics. These cannot be your sources, These can give you the idea, but you'll need to get your source elsewhere. All right, preliminary questions. What is the definition of a critical point?
Where it's either undefined or
What is?
Where the first derivative
Is
is
either
equal to 0 or it's undefined.
Undefined. Perfect. Okay. And questions 2 and 3 choose the correct conclusion. Okay. Number 2. If f is not continuous on 0 to 1, then either A, f has no, oh, you don't have a book, so let me write this down, because these are hard to remember. All right. Number 2 starts with if f is not continuous on 0 to 1. F not continuous on the interval 0 to 1. Okay? That's what's given. Then which of these is the correct conclusion? A, f has no extreme values on 0 to 1. Or B, f might not have any extreme values on -1. Extreme values, so I'm just going to put EVs on 0 to 1. Which of those would be the correct conclusion? If f is not continuous on that, does that mean it has no extreme values, or it might not have any extreme values?
So does that mean it's like that there's a hole in the graph?
It could be a hole in the graph.
Or
It
could
could
be
be
a
jump in the graph,
piecewise,
right? It could have infinity in the graph. I mean,
Right.
any of those could be the case.
Well, in that case, would it be that there's no extreme values?
Well,
I'm just thinking of a piecewise, if it's broken up into different sections.
okay. So if it's piecewise, let's say it does this and it does that. Okay, well then that could be an extreme value. That could be an extreme value.
Okay.
Yeah. So I think you'd have to go with might not.
Right.
Okay, now that's my guess. Let's see what the book says. By the way, the first one, 4.2, preliminary questions. Critical point is A. Yeah, we got that one right. And the number 2 is B. Right.
So I guess in a sense, even if you have, I mean, if you have a point,
Right.
that can be an extreme value.
Yeah, you mean just the function could be defined just to be, yeah,
Right.
that could, if
Just
that's the
how-
maximum or minimum value in that interval, then that's an extreme
So
value.
if it's coming and it
Oh yeah,
has a point way up at the top, you see what I'm saying? If it's
Yeah.
converging and then it has a point up at the top,
Right.
that would still be
an extreme
an
value.
extreme value.
Whereas if that approached infinity but never had a point, that would not have an extreme value.
Gotcha. Okay.
Okay, unless it had a minimum, you know.
Right.
Okay, so the 2 is B, this is 2, this is 3. If f is continuous, but it has no critical points, really ugly writing on 0 to 1, then which of these is your conclusion then? F has no min or max on 0, 1. Or B, either f of 0 or f of 1 is a minimum value on 0, 1. Okay, what you think? Says that f is continuous, but has no critical points on 0 to 1.
a straight line? Is that what we would be visualizing? If it didn't have any critical, so there's not an extreme.
Okay, a straight line would be an example of that. No critical points there. Wouldn't have to be a straight line, but it could. This one is not a straight line, but it has no critical points.
Right.
Okay. So yeah, you got the general idea.
So
Okay.
would it be? Yeah, would it be B?
It would have to be B.
Either
F or 0 or F of 1 is your minimum value, the other one's going to be your maximum value.
Yeah.
Yeah. Okay. Exactly. All right, good deal. So, pretty sure the back of the book said B2, but let's just check and see. Sure enough, well, let's see. Yep, 3B. Good deal. Number 4. Fermat's theorem does not claim, okay. Now, we did Fermat's theorem a bit earlier. That's on the bottom of page.
It's also in the summary, too.
Yeah, oh yeah, it's right there. I forgot that. Okay, there it is.
It's the fourth one. That's the fifth one down.
Okay, yeah. Back one page. Yeah, Fermat's theorem, if f of c is a local max or min, then c is a critical point. Okay? Now, what 4 says, Fermat's theorem does not claim that if f prime is equal to 0, then f prime of c is equal to 0, then f of c is a local extreme value. That's false. What does Fermat's theorem assert? And yeah, if you just go back and state it. Yeah. Okay. All right, homework exercises here. Do 1. Okay? Then do any of the odds 3 through 19. Then do any of the odds 21 through 27. Now, some of those, like 25 says you need a graphing utility. If you do need one, you don't have one, don't sweat it. 27 says you need a computer algebra system. If you can't do it without one, then don't sweat it if you don't have that access to that. Then do any of the odds 29 through 57, a whole bunch of those. Then do 59, try to do that one. Now the last two parts say, the last part says you need a graphing utility. Then do either 61 or 63 or both, that's up to you. And then either 65 or 67 or both, that's up to you. And then do any of the odds 69 through 75. No, I'm sorry, looking at the wrong thing. 69 through, wow, they just keep on trucking, to 81, okay? Now back off a little bit there, and you'll see a couple of things in there. In 77, it talks about Betts's function. So who in the world is Betts, or what was his function? And, oh, there he is, Alfred Betts, 1919 physicist Alfred Betts, argued that blah, blah, blah. So there's a, by the way, that's maximum efficiency of a wind turbine. Boy, we thought wind turbines were fairly recent. 1919 they were studying those. So that's a fairly, even though it's a long time ago, current topic. And then the Bohr radius is mentioned. That's getting into some quantum mechanics, but if you did want to write on that, you certainly could. Resonance curve, resonant frequency, you could write on either of those if you wanted to. And so anyway, let's go. Do number 83, and then any of the odds 85 through 89. But also glancing there, number 90, which you don't have to do, but it deals with Snell's law. So who in the world was Snell, and what does that have to do with anything? And certainly that's
what,
the refraction.
yeah, the
Yeah.
guy who's spoken physics class.
Yeah. Exactly. And rainbows, that kind of stuff. You can look at further insights and challenges. If you want to do any, you certainly can. I usually look at these to see if there's any additional paper topics there. All right, now we are rapidly running out of time, So what I think I'm going to do, sorry, I'm hitting the wrong slide here. Let me just advance. Okay. Okay. Let's move on to 4.3. And I think what I'm going to do is sort of go quickly through this. It's pretty straightforward stuff. We just won't stop and do lots of examples. Why in the world this is having so much trouble opening, I don't know. It started to open and now is sitting there. So let me see if I can find out why it's doing weird stuff. Okay, that doesn't help me any. So I think what I'll do is escape. That doesn't help. Yuck. Why is it getting hung up? I think what I'll do is this, and I hate doing this. Why is that in there? Okay. Nope.
Closing the window. Go on the PowerPoint thing again.
Down here?
Yes. And then go up.
Oh yeah, and close here.
And then close, yes.
Okay.
That'll do it now.
Now we got to start back over. Yeah. Okay.
I don't know if it'll work or
No, it should. Up here. I'll just have to go through all this again. It's doing the same thing. I wonder if my disk is
I was going to say it's
corrupted.
Scratch the word.
Huh?
I was just going to say, is the disk scratched?
It hasn't had a problem before that I know of.
That is pretty strange. Try
Yeah.
clicking on the next one. See if it'll.
Let's see. Do the previous one because we were just there. Oh, let's go back and close this one out again. Let's see. Well, I don't know. Nothing's opening now.
I heard the disk that time.
Yeah, so it did. Let's close that one. Let's try this.
Oh,
Ah.
hey, there we go.
Okay.
That was strange, though, but I mean, huh.
All right. Now, we just did Rolle's theorem, which basically said if you have a continuous function, differentiable function, and f of a on the interval a to b, f of a is equal to f of b, then somewhere in between the first derivative is 0. Mean value theorem does something very similar to this. You still have to have a smooth continuous function, differentiable function. But here on the interval a to b, f of a and f of b don't have to be the same value, but what they do say is there exists at least one tangent line that's parallel to the secant line between a and b. Okay? It's just that Rolle's theorem had that being horizontal. This has it being anything else. And again, if it's smooth and continuous, that's got to be true. If it's here, then either it's going to be coming down like this, which would have a value down here, parallel, or one up there, or it can have many of them in between there. But there has to be at least one tangent line parallel to the secant line. The secant line being Sorry. The line with the slope f of b minus f of a over b minus a. Okay. Remember that. Now, let's do, I said we weren't going to, okay. Here's a statement of the mean value theorem then. So let's get that documented here. This is mostly for people not here. Mean value theorem, also Rodney, since he does have his book now. Assume that f is continuous on the closed interval a to b and differentiable on the open interval a to b. Then there exists at least one value in a to b such that f prime of c, that value c, the f prime of c is going to be half the slope of that secant line. F of b minus f of a is change of y over change of x, b minus f. So that's going to have that slope there. That's the mean value theorem. Okay. And a very useful theorem, by the way, too. They do a little conceptual insight here. Let's see if they do that. Yeah, they kind of do. This is sort of part of the proof of it. If this is your A, here's your A, there's your B, there's f of A, there's f of B, then the slope, f of A minus f of B over B minus A, that's going to be that slope. If you did parallel lines up here until you reach some point, because the function has to be smooth and continuous, it's got to be some point where it becomes a tangent line. Okay, almost sort of like our limits before, but not quite. I mean, but fairly similar. Move the secant line in a parallel fashion until it becomes a tangent line. That's another way you can look at this. Okay. Here is yet another way. This is in the conceptual insight that's on the bottom of page 210. And that basically says that if f prime of c is equal to f of a minus f b over b minus a, multiply both sides of this, and basically what you have is a point slope formula. That's what this turns out to be. y2 minus y1 is equal to L times x2 minus x1. Okay, point slope formula. So that's another way to do it, only in terms of derivatives rather than slope. So there's lots of ways to think of the mean value theorem, and just about all of them are pretty useful. Let's do example 1 here. I think we can pretty straightforwardly. Okay. Verify the mean value theorem where f of x is the square root of x. There it is right there. Okay. A is equal to 1. Okay, right there, 1, 1. And b is equal to 9. That would be 9, 3. So there's your 2 points there. So it says first compute the slope of the secant line. So in order to get, I gotta change my color back. Okay. So the slope of the secant line, f prime of c, is going to be f of b, which that was 3, right, minus 1 over 9 minus 1, which would be 2/8, which is 1/4. Okay? Now, it says verify the mean value theorem with f prime. So, what would we do here? This is your function. I would write that as x to the 1/2. I don't like taking derivatives of radicals. I like taking derivatives of exponents. So write it in exponential form. So f prime would be what?
So 1/2 x to the negative 1/2.
Okay, very good. Now, we need to find a place where that has a value of 1/4. Okay, So set this equal to 1/4. And I think we can multiply both sides of this equation by 2. And that would give us, actually I'd say by 4. That would give us 2x to the minus 1/2 is equal to 1. Okay? In this case,
Gotcha, you just multiplied. Gotcha.
Yeah.
Cool.
Okay. And in this case, I think I will write this back in radical notation. This will be 2 over the square root of x is equal to 1. And then what?
You multiply by square root of x.
Yep. That's square root of x. Square root of x. These go out. You have 2 is equal to square root of x. And guess what x would be then?
Square root of 2, right?
Nope. 2 is equal to square root of x.
Oh, you would square it.
Square both sides, 4.
Okay.
Okay. So x equals 4, and sure enough, x equals 4 is a value in between 1 and 9, and at that point you do have the tangent line equal to, the slope of the tangent line equal to that secant line. All right, very good. Now, this mean value theorem also has a corollary, which means something else that also implies that you might not think about right off the top. That's not really the definition of corollary, but that's how I like to think of it. If f is differentiable, that's what we've had before, and f prime of x is equal to 0, for all x's in an interval a to b, then f of x is a constant on a to b. Yeah, if the first derivative is 0 everywhere on a to b, in other words, f of x is equal to some constant c everywhere there, because that's the only way the first derivative is going to be 0, is f of x is a constant. So that's a corollary of this. There is a little proof there. Go for it. Now, with that in mind, and if you notice what the title of this section was, the mean value theorem, that's what we've been talking about, and monotonicity. What? Monotonicity. In other words, something is monotonic. Okay? Well, here's what we mean by that. Yeah. Well, sort of skipping, before you get to the theorem, it says, we prove now that the sign of a derivative determines whether the function is increasing or decreasing. Man, it seems like we've done that before, okay? But if a function is increasing on some interval a to b, then, and it's always increasing there, then the derivative, okay. No, okay. Here's what it says, recall. If a function is increasing on a to b, that means that f of x1 is always less than f of x2 for every x1 and x2 on the interval a to b when x1 is less than x2. If it's a decreasing function, then f of x1 is always greater than or equal to f of x2 if x1 is less than x2. So those are the definitions from a long time back. We say that f is monotonic. Mono means one, monocle, okay, one lens, okay, monotonic, okay, on a to b, if it's either increasing or decreasing on a to b, but not both. So that then leads to the second theorem, okay. All right. Let f be a differentiable function on an open interval a to b. If f prime of x is greater than 0, in other words, the slope of this curve is always positive, then that function is always increasing. It doesn't have to be a fixed value, it's just never negative, then f is increasing on a to b, meaning it's monotonic on a to b. If f prime of x is always negative, even though it's not always the same value, but it's always less than 0, for x from A to B, then f is strictly decreasing on A to B, meaning it's monotonically decreasing on A to B. Okay? And there's a little proof, and it's not a bad one to do. But here are a couple of examples, figures in figure 4. Okay, now, in the book, they're written one over each other. This makes it look like it's one function. It's not. These are two different scenarios here. Okay?
Yeah, that is kind of weird how they...
Right. This almost makes it look like this is a one function, but it's not. This is an increasing function. So, I mean, whoops, that's not what I meant to do. Right. Well, wait.
I think you just went forward the slide.
Yeah, I was trying to get back to it. I kept hitting the wrong key. What I'm going to do is this.
There we go.
All right. A little bizarre looking, but this is a function that's increasing. The tangent lines, no matter where you are always positive. Extraordinarily positive here, slightly positive there, but never negative, and never zero. So that's an increasing function. Okay? And this is the one I was trying to hit before and I hit the wrong key. The decreasing function, if I carried it on over here, so that's out of the picture, then this is the decreasing function, that the derivatives, the slopes of the tangent lines are always negative no matter where they are. Up there, extraordinarily negative, down here, slightly negative, but always negative. So that's always a decreasing function. Okay. Now, here is theorem. This is the graph for example 2. Show that f of x is equal to log x is increasing. So here's your function. Y, or f of x, is equal to log x, okay, is always increasing. How would you show that? Take a derivative, okay? So y prime, or dy dx, or df dx, however you want to call that, is equal to?
X,
1 over x. That's the derivative of the log function. And if x is always positive, okay, which x can't ever be 0, of course, right? And we're not going to let it be negative here. Well, it can't be negative. So log x is not defined for negative. So this is, x is always positive. So no matter how small it is, that's a very positive line if y prime is very positive. But even when x is extraordinarily large, 1 over x is approaching 0, but it's never 0 and is always slightly positive. So sure enough, that is strictly an increasing function. Okay, log x is always an increasing function. The larger the x is less the rate of increase, but it's always increasing. Okay. I think this is example 3. Okay. Yeah. Find the intervals on which f of x is equal to x squared minus 2x minus 3 is monotonic. Find the intervals over which they are. Huh?
Did they skip example 2?
This is example 3, right.
That's why I'm asking, did they skip over example 2?
No, example 2 was log x.
Oh, that's
Yeah.
my bad. My book's a little different.
Okay. All right. So it says find the intervals for which this function is monotonic. So what would you do? Take the derivative. F prime of x is equal to 2x minus 2. Now we want the places where this is strictly increasing and the places where it's strictly decreasing. So what might be an interesting thing to pick?
How about
0,
0?
yeah, where it's neither increasing or decreasing. First set that equals 0, where's that going to be?
-2. Or, excuse me, 7. So, -1.
Okay, x equal minus 1. No, how about just 1?
That's right, because you add. Sorry.
Yeah, right, okay. X equal 1, okay. So one side or the other of x equal 1, it's probably doing one and probably doing the other. So how do we tell? Pick a number to the left of 1, which would be a real easy one.
How about 2?
Left.
Or how about negative 1?
Okay, even easier.
0.
0, why not 0? So plug in f prime of 0, and what do you get? Negative 2. So what's it doing to the left of 1? Decreasing. And always decreasing, okay? Because that's the only place it's going to be 0. And then, like you say, let's choose f prime of 2, something to the right. So that's going to be a positive 2, so it's strictly increasing anywhere to the right. So it's strictly decreasing anytime x is less than 1, and strictly increasing anytime it's greater than 1. Monotonically decreasing for x less than 1, and monotonically increasing when x is greater than 1. At x equal 1, it's doing neither one because there your derivative is 0. Okay? How are we doing?
It's just now 11, 12.
Okay, so I think
we have until 11, 15, right?
no, I think it's 11, 10.
11, 10, okay.
Yeah, I think we've just gotten there. So there's my pencil. So we did example 3. We'll pick up next time with testing critical points. Okay? I didn't go as fast as I wanted to here, but 4.3, I think you can do any of the odds 1 through 7. I think you can do 9 or 11. And I think you can do any of the odds 13 through 17. And we'll stop there and pick up the rest of those next time. Okay, let's just give a quick and dirty here of what we got left to do. Okay? I want to for sure finish 4.3 and 4.4. Those are pretty important. We'll try to go through those pretty quickly. Okay? 4.5, L'Hopital's rule, you'll use that repeatedly, so I want you to be sure you have that one. That's 4.5. And graph sketching and asymptotes, we hopefully will at least get to that, and we'll probably just skip applied optimization, which is a really good section, but I don't think we'll have time to do that. Newton's method, even if we don't do it, I want to at least show you that. It's just an incredibly fantastic little thing, procedure. And that's it. And so I'm guessing at the end of 4, we'll have, I'll try to get as much covered as possible, and your last test will be just on chapter 4. Now, I'd really like to introduce you to the stuff in 5. Because when you start Cal 2, you should at least have hit the first part of chapter 5. We lost a week and a half this term because they started class on a Tuesday rather than a Monday or a Wednesday, which hurt us. Then we had Martin Luther King Day off, and Tuesday, Thursday classes didn't. And then we had a weather day. That was a Wednesday. So we've lost a week and a half. So I'm going to try to, the last day of class, go a quick and dirty on the first part of chapter 5. Okay? I hate to do it that way, but I want you to have some exposure to it before you get to Cal 2. Okay? I wish we had time to do 5.3, which is the indefinite integral. I don't know that we'll have that because I think Cal 2 usually starts with fundamental theorem of calculus part 1 and part 2, or definite integral 1. I don't remember which. Part 1 is definite integral, basically. But if you, I think I'm scheduled, let's see. Yeah, I'm scheduled to do Cal 2 in the summer if enough students sign up for it. And if you do, I'll start with where we leave off. If you go somewhere else, you may be starting beyond where we leave off, so.
I've already signed up.
Yeah.
Paid, so
Okay, for Cal 2 here?
yep.
Okay. All right. Hopefully we'll get enough to make, but right now the numbers aren't looking good. All right, good deal. That was it for today. Went a little over. And did you need? Yeah, okay. Let me.